You've been jumping your whole life, but change gravity and the same body can barely leave the ground or fly. The Sun and Jupiter, where jumping becomes embarrassing. Surface gravity on the Sun is 28 times stronger than Earth's. That means every kilogram of your body feels like 28 kilograms. Your legs are still yours and your muscles are the same. But the force pulling everything back toward the ground is overwhelming. A jump that gets you 45 centimeters on Earth gets you about 1.6 centimeters on the Sun. That's less than the thickness of your thumb. You would push, feel almost nothing happen, and land again before you registered leaving the ground. Of course, you'd be ionized in milliseconds. The jump is entirely hypothetical. The surface temperature is also 5,500 degrees Celsius, which makes the jumping question somewhat theoretical. Jupiter is the biggest planet in the solar system. If you had something solid to jump from, its gravity would still limit you to about 18 centimeters. Your legs put out the same force they always do, but Jupiter simply outweighs them. Without a suit, you'd lose consciousness within seconds in the toxic upper atmosphere, and the pressure would finish the job within minutes. From here, it gets more interesting. The next 5 worlds have gravity so close to Earth's that you'd barely notice the difference. Neptune, Saturn, Earth, Venus, Uranus, the middle of the scale. 5 worlds, 5 different distances from the Sun, 5 completely different compositions, and your jump height across all of them fits inside a 10-centimeter range. Neptune pulls slightly harder than Earth. Its gravity is about 1.14 times ours. A jump gets you about 40 centimeters. You'd notice the extra pull, feel a little heavier, but still move and walk and jump in ways that feel recognizable. You'd also lose consciousness within seconds in the freezing, unbreathable atmosphere, and die within minutes. But the jump itself would be almost familiar. Saturn is the second most massive planet in the solar system. Here's the part that catches people off guard. Its gravity at the cloud tops is only slightly stronger than Earth's. Because Saturn is extraordinarily low in density, it's so light relative to its size that it would float in water technically. A jump on Saturn gets you about 42 centimeters, just slightly less than Earth. Your first reaction would be, is that it? Your second reaction wouldn't happen, because you'd be unconscious within seconds and dead soon after. Venus is Earth's twin in size and mass, with about 91% of our gravity. Jump height, about 50 centimeters, almost identical to home. The atmosphere would collapse you within seconds from the heat and pressure alone, and kill you within minutes. Uranus, same story. About 91% of Earth's gravity. A jump gets you about 50 centimeters. You'd lose consciousness within seconds in the upper atmosphere. Dead within minutes, 50 centimeters. Earth, 45 centimeters. You survive. That's the deal you have here. So the question is, why do 5 planets spread across the entire solar system all give you roughly the same jump height? The answer is that gravity depends on both mass and radius. And across this group, those 2 numbers happen to cancel each other into a narrow band. The universe landed on near-identical outcomes through completely different paths. Earth is the reference point, the middle of the scale. What you feel every day is just one setting, and the solar system has far more extreme ones still to offer. Mars and Mercury, the first taste of freedom. Mars changes everything. Mars has about 38% of Earth's gravity. A standard jump sends you 1.2 meters into the air, above most door frames. You'd hang there long enough to look around, choose a landing spot, and feel genuinely weightless for a moment. On Mars, every step sends you slightly further than expected. Every jump gives you a full beat of airtime you've never had before. A slow walk feels like gliding. A run feels like something athletes dream about. In the thin carbon dioxide atmosphere, you'd lose consciousness in 10 to 15 seconds and die within 2 minutes. So you'd get maybe 1 run before that happened. Mercury gives you almost the same jump, but for a completely different reason. It's smaller than Mars and much lighter in mass, but it's also far denser, with a huge iron core packed into a much smaller world. So its surface gravity ends up almost identical to Mars, at about 38% of Earth's. Same jump height, same floating sensation. But on Mercury, that feeling ends fast. In the near vacuum, you'd be unconscious in 10 to 15 seconds and dead within 2 minutes. The float would end before you landed. People assume smaller means weaker gravity. Mercury breaks that assumption. Density matters just as much as mass, and Mercury packs a lot of it into a very small space. This is the threshold. Cross below this gravity level and the body starts discovering what it could do all along. The solar system still has much lower to offer. The moon's getting genuinely strange. The moon has 1/6 of Earth's gravity. A good jump reaches 2.7 meters and keeps you airborne for almost 4 seconds. That's enough time to rotate your body, take in a full 360-degree view, and plan your landing. The Apollo astronauts experienced this directly. Buzz Aldrin discovered the most efficient way to travel was a series of small bunny hops, because standard walking wasted energy and normal running felt too unpredictable. They had to learn movement from scratch. In the moon's near vacuum, consciousness goes in 10 to 15 seconds, and death follows in under 2 minutes. The astronauts needed their suits for exactly that reason. From here, the moons show how strange movement gets when gravity keeps dropping, for the few seconds you'd have to experience it. Io, Jupiter's violently volcanic moon, has the highest surface gravity of any moon in the solar system. A jump reaches about 2.5 meters. The atmospheric conditions would take you out in 10 to 15 seconds, same timeline as the moon, but at least you'd clear a doorframe first. Ganymede, the largest moon in the solar system, gives you about 3.1 meters of air. Near vacuum. Unconscious in 10 to 15 seconds. Dead within 2 minutes. Still, 3.1 meters is no small jump. Titan sits next, and Titan is the exception. Its thick nitrogen atmosphere means you'd stay conscious for 30 to 90 seconds before the lack of oxygen caught up with you. Death would follow within minutes. But those 30 to 90 seconds would be the longest window anyone had unprotected on any other world. Gravity there is only about 14% of ours. So in the same basic gravity calculation, a jump reaches about 3.3 meters. The thick air would complicate the motion and slow everything down. You'd descend slowly, almost floatingly through orange fog. It'd feel like jumping inside a very large, very cold swimming pool in slow motion. And on Titan, you'd almost have long enough to enjoy it. Europa and Callisto push the numbers slightly higher again. Europa gives you about 3.4 meters of jump height. Callisto gives you about 3.6 meters. Both are near vacuum. Both 10 to 15 seconds to unconsciousness, 2 minutes to death. Here's what that sequence actually means. You'd jump and have time to look sideways. Time to look down. Time to register that the surface is not rushing back up to meet you the way it always has. The moons mark the point where jumping stops being a physical act and starts being a sensory experience. And the numbers are about to leave the moons behind entirely. Triton, Pluto, Ceres, the numbers get absurd. Triton, Neptune's largest moon, sits at about 8% of Earth's gravity. A jump pushes you to around 5.7 meters. You'd spend the descent watching Neptune fill the sky, enormous and blue-green, close enough to feel real. Unconscious in 10 to 15 seconds. Dead within 2 minutes. The view would be brief, but extraordinary. Pluto's surface gravity is about 6% of Earth's. A standard jump reaches about 7.1 meters, around 23 feet, and keeps you in the air for 9 to 10 seconds. In Pluto's near vacuum, you'd lose consciousness in 10 to 15 seconds and die within 2 minutes. So the jump and the death have roughly the same timeline. You'd go unconscious somewhere around the descent. 10 seconds is a long time. Long enough to have a thought, change your mind about it, and have another. Long enough to watch the horizon tilt slightly as Pluto's tiny sphere rotates beneath you. Long enough to understand that the rules you grew up with have been suspended. Ceres, the dwarf planet in the asteroid belt, has gravity just under 3% of Earth's. A good jump clears about 16 meters and holds you up for about 22 seconds. In a near vacuum, unconsciousness arrives in 10 to 15 seconds. You'd wave at that asteroid and be gone before you landed. At this level of gravity, the body gets confused in a genuinely useful way. Your legs fire with the same force they always have. But the ground has stopped cooperating. The jump becomes a conversation between your muscles and a world that's barely holding you. Enceladus and Phobos, where it stops being a game. Enceladus is Saturn's small, icy moon. It has a liquid ocean hidden under its frozen crust and regularly fires geysers of ice hundreds of kilometers into space. Scientists consider it one of the best candidates for finding life beyond Earth. The moon is basically already trying to get your attention. And on its surface, your average jump reaches about 39 meters. That's about 13 floors. You stay in the air for about 52 seconds. In a near vacuum, you'd lose consciousness in 10 to 15 seconds and die within 2 minutes. So you'd be unconscious high above the surface on the way up and dead before you landed. But the jump itself would still happen. Almost a minute of physics whether you're awake for it or not, floating above an icy world, watching the rings of Saturn arc across the sky, geysers erupting around you, then landing with exactly the same impact you'd feel stepping off a curb on Earth. Phobos is Mars's inner moon, only 22 kilometers across. Its gravity is so weak that your legs could launch you about 764 meters into the sky. The trip takes just over 17 minutes, but in vacuum, you'd be unconscious in seconds, dead within 2 minutes, and Mars's gravity might keep you from ever landing again. A single enthusiastic jump on Phobos could strand you in orbit, and you would never come back.